Uh, as I turn off the stream, and I've started my find here. Let's just say that I'm a bit stupid, because this right here is where I tried doing the alias and trying to find stuff, and then I didn't find anything, and then I tried to go to lost and find, and there was nothing there, and I was confused. That's because I'm on the server. I SSH'd into it, for fuck's sake. There it is! Well, welcome to Windows XP! That's not how full screen works. This is how full screen works. If it would do anything. Yay! Welcome to Windows XP. Yeah, this is a bit more closer to what we're doing today. We're not gonna go quite this far and emulate Windows, but we're gonna emulate a very small CPU in a recompiled way instead of a interpreted way. Well, recompiled as it's seen from Python. Also, the sound, you're not gonna be able to hear it, but it's horrible and you don't want to hear it anyway. Yes, you don't want to hear that. It's glitchy and bad. But hey, look at this, we have Windows running on Linux with actual stuff. Vänta! I don't get people at all sometimes. Screaming like the world is about to end and then like, oh, we're going away now. What? Yes, so? Nothing I already knew. Anyway, what I was gonna remark with this emulator right here is that it's KVM enabled. What does that mean? Good question. It is. Oh, it's. I gotta do that. Okay. Well, if you can read this, it's actually emulating the CPU that's inside this physical computer. It's using the. I think at least it's using the actual CPU to execute the actual instructions, although in a sandbox environment. Oh, they might not be that when they read up on this. But what I do now know is that KVM is stands for kernel virtual machine, and that essentially means that this machine right here has direct access to the kernel functions that that the processor has enabled. So this processor, this Windows XP installation essentially, it essentially has an Intel R Core i7-4790K in it, but it's not a real one because it only has 2 cores. Also, why are you using the page file on the desktop? Why you put 107 megs in the page file? What? You have RAM. Is that what? I don't even know how much RAM I gave this. I think I gave it 3 gigs. And yeah, this works like any other computer. You could play pinball. And I now realize that my microphone is actually on the... It's on the table in front of me, so you can probably hear this quite well. I'm sorry. There we go. You can hear me better again, I guess. But yeah, this is... Ow! Volume could be better. Okay, ouch. I'm just gonna quit this now. That's a horrible sound. Don't get me wrong, the XP startup and shutdown sounds are awesome, but when they're rendered with broken bit rates and interrupt failures, it's less than pleasing. Let's just say that. So with that little trip, oh wait, I saw something there. Could I open that again? Can I just do creators? Does that work? No. Rip. Rip and pepperoni. So it did become its own video. I'm gonna have to rename that. Rip. That sucks. Na says, are you writing an emulator? Yes, I am. We were just, I don't know, emulating some other stuff at the beginning and actually starting a server and pinging it and stuff and just your normal day stuff, I guess. Depends on who you are. So, let's get to it. Let's open our Sublime. And why did I close the terminal when I clearly need one? So, last time we were in Ben Eater's CPU and we were in the interpreter. Now we're gonna create Ben Eater CPU. No, not SPU. CPU recompiler. Yes, we're doing that. What are we gonna need? We are gonna need our main file. We don't need a run. We can probably steal this right here as our counting down program. We can steal that. We can steal this entire file, to be honest, and let's touch. Ooh, do we want to though? I'm just gonna keep it to main.py for now. So, this should run flawlessly. See, did jack shit. Probably want to define this as a class. Or do we? I mean, either we compile the code and run it in this global scope, or we compile it and run it in a class which is contained, so we're gonna run it in a class. Really, the choice is yours, do whatever the fuck you want. As long as you can connect things and be reasonably clear about it, and as long as you have a good naming scheme, you should be good, and you shouldn't need much comments, to be honest. Preferably none at all. So we're gonna have a class here, and we are, I guess we can call this recompiler, because that's what it's gonna do. I'm thinking way too far ahead, but you need to do that sometimes because you need to be able to see problems in advance. And I can't really walk you through this like thought process, but what I'm essentially doing is I'm thinking like, okay, what should this recompiler do? And well, it should recompile, it should take the RAM that we gave it, that's the program space, and we should... oh no, this won't work at all. Oh no, we can't recompile. Because of the combined program and data RAM, there's a possibility that you could do STA into the onto the address that's just after this, and you could have your input to that store like be a subtract or add or any like condition, and that would change the program path theoretically. Speaking of which, if we would take this, just theoretical here, and we're wearing a bit off track, but stay with me. If we would take Benito's CPU here, and if we would expand its capabilities so that it has n amounts of RAM and n amounts of address space, or yeah, whatever, and it can work with n amounts of bits, and because you can interact with the data you execute from, that's the feedback loop I talked about at the end of 1.5, you essentially can have the program, based on what it does before, change its next state, which is the very definition of a state machine. So this computer technically is Turing complete, because moving data is technically being Turing complete if you're being smart enough about it. And yeah, I don't really know what I was going with that. This Benito's CPU is Turing complete, but it's you have to make it Turing complete by assembling these instructions in a very specific way, and there's no individual instruction that in of itself allows for easy control. You have to build your control from all of these primitive functions, from all these primitive opcodes. So yeah, technically the description is wrong, but for all intents and purposes, it's practically correct. So yes, back to this. How should one? And that's the thing, because we can take a value from our program space and muck it about and add it, subtract it, whatever, and then write it back to memory and then execute what we have mumbled around, we can't recompile it, because when we recompile, we are statically recompiling. The thing expects that stuff will be where it is, whereas in that was not a good explanation at all. When you're statically recompiling stuff, you assume nothing is going to change. But since this CPU can change its own program flow by just writing to RAM, because that's where the program lives, you essentially have a function behind that modifies a function in front, maybe, depending on its own input. And sure, you could, for this small, very, very small address space, you could pre-execute it, but then it's not a recompile anymore. Then it's a step. Then it's not a recompiler, that's for sure. So how would one make a recompiler in Python, if that's even possible? The thing is that we could make this just-in-time compiler, but that's essentially this. It's essentially the same, but instead of having the opcodes defined as a function, they're essentially defined as strings, like so, like literally like return that and then execute it. That's as close we can get to just-in-time compilation in Python. If we'd actually want to do recompiling, just-in-time compiling, just-in-time intermediate language compiling, we'd have to jump into some more complex language, I imagine, like C. C, I guess. So essentially, to bring it down to a conclusion, because we can't really continue from here, I'm sorry, is that given the levels of abstraction we have here, we have emulators, and then within emulators we have the different types of emulators. Now, when we're using a high-level language like Python, we can't really get into the nitty-gritty and tell the processor what to do, like we would need to do if we were doing a recompiler or a just-in-time compiler, or even a just-in-time intermediate language compiler. So literally we have reached the abstraction limit for Python here. This is essentially the only, well, it's one way to write an emulator in Python, but in a way it's all of them at the same time, because hey, look, it's interpreted because it just executes an instruction that does what it just takes the, it just emulates being it. That's what emulator comes from. It pretends, and it's just in time because that's how Python works underneath, I think. And it's just in time intermediate language because technically Python is compiling to Python bytecode, and then that Python bytecode is interpreted by the Python runtime thing, whatever. It's weird, but to say the least, this is basically the abstraction limit with Python. You could, you could write this emulator in, as I said, in a number of different ways. You could just return strings and then execute them strings. But you can't, and that would be a just-in-time compiler. You can't really do a recompiler because you can't really statically recompile a program that executes from its own data RAM, or it gets data from its own program RAM. It's a feedback loop there that makes inconsistency. It's an inconsistency when it comes to actually executing values you write back, but other than that, it's not a problem, I guess. If you're testing programs that don't write to addresses where your program executes, you could write this emulator so that you essentially step through the RAM. Where would that be? Here. You step for the RAM, you map this to a piece of string, and you take all of those strings, one after another, and just slap them together, and then you just put that big string and execute it. Well, you evaluate it so that it gets compiled, and you put it into a function, and then you just execute that function, and now you've executed the RAM once, whatever that means. So yeah, we've reached abstraction limits, and I thought this series was going to be longer than this, but apparently not. So that's been it, I guess. Not much more to tell, except for when Ben implements, I guess it's going to be these two right here. It's going to be a jump if carry and jump if zero. And when he does that, I'm going to have to change some fundamentals on how this works, like in actually including an accumulator and some flags. But other than that, this series is done for. We can't really get in the more complex without changing the language. And that's kind of sad because Python is easy to read and understand. At least for me, and hopefully for most of you. Yeah, I will stop rambling. This was a useless stream. Goodbye.